That'll get you ready for today's activities. When you have those installed, put your blue tab up. If you're having trouble installing, put your orange tab up. I've never played Wordle.
You want to change echo to equal true, equal false.
It's already true in mine. That's just when you open up an R Markdown, it has all this introductory stuff at the beginning that you don't really need. So I typically delete it. You see that there's nothing above that. I sometimes leave myself this last little reminder that echo is a command that I can use to hide code chunks. Sorry, do you still need the packages? Yeah, they're there. Blue tabs up when you've installed effectively. Oh, are you having an issue?
Yeah, it's not letting me change.
Get WD. Clear haze. All right, so now you're trying to change it to that. Get rid of everything from clear haze back.
Do I need that first step?
Nope, shouldn't. I don't think so. Okay, maybe you do need that first slash. Okay, that's weird. Go to that directory you're trying to link to. I'm sure you've already done this. Click on it, right click on it. Get info, get the path. This is the path you're going for, not users. You're accessing something that is on your iCloud.
Mm-hmm.
So you need your iCloud address in there, not. So it wasn't users Claire Hayes, it was iCloud. Go back to your folder. This is your path. It's your iCloud drive. So just copy that. Copy that thing. Paste it in there, but leave the DTS218. That's weird.
I've done it like this on everything else, even though it says iCloud.
Okay, try that again then. That's just bizarre.
It
Okay, there it goes. All right, blue tabs. You fix it?
Just fix it.
Okay, all right, cool. Yes, ma'am.
On the package, I don't think I'm typing.
Yeah, on this.
It's just doing nothing when I try to run it. Is this how you do it in the print?
Yeah, should be. Pload and everything in parentheses. That's weird.
It's not typing.
Oh, why is it not typing? Ah, I did something. Erase. Load library Pac-Man, just to make sure. Nope, library.
Library?
Library. Library. That's how you call up packages. Okay, why is suddenly R totally non-responsive? Try activating it there. All right, save. Put it in that directory. Close our, and then open that script. Did you get everything to install? Okay, blue tab up then.
Just getting everything in. I'm all
Okay,
set.
all right. Everything installed?
I had to restart it. So
Okay.
I'm just retyping it now.
Okay. All right. Still doing that?
Yeah. It just doesn't want to do it.
All right. That's weird. It's almost as if your keyboard isn't functioning. So were you able to set WD?
That was working.
Okay. This is stupid. Just so you know, I think this is stupid. Wait a minute. Where's the end of your?
Missing a parenthesis. Oh. Is that it?
You have to finish off your code chunk. I don't know why maybe you deleted it when you highlighted something. Yeah, that's the reason.
Thank you.
You didn't finish off your code chunk. Okay. All right, cool. All right. Just reduce your screens or leave your screens where they are or whatever. I have a couple more things I want to talk to you about two-way analysis of variance. You can take your tabs down also. So over the last couple of days, we've talked about the difference between replicated and unreplicated two-way analysis of variance, but I skipped to unreplicated from replicated so that you could see the difference. I want to go back to replicated two-way ANOVAs to talk to you about the last thing that we kind of need to talk about here. So you'll recall that in this case, we were looking at the growth of rats when we feed them different kinds of food in this textbook example. And we have two factors here. We have the type of food that we're feeding, and we have the sex of the rats. And we generally refer to in statistics as these things as factors. You'll note that in R we oftentimes have to code variables that we have in our data frames as dot factor, and that's what we're telling R is that we want you to treat that particular variable as a factor as opposed to an integer or something else. So factors can be one of two types. They can be what we call fixed effects factors, or they can be random effects. And this is important because it changes how you calculate the F statistic when you go to test the hypotheses. If you're going to test, typically we test things by calculating an F statistic where F is calculated as the mean squared of whatever the effect is divided by the mean squared within, or error, or residual. You will see this called this same thing in multiple places, different things. In R, we generally refer to this as the residual term, but it's the within sample error term. But when you have a fixed effect, you generally do this. But when you have a random effect, you generally calculate F by dividing the mean squared effect by the mean squared interaction, the interaction term of the ANOVA. So remember that when we have an ANOVA table, here are the two ANOVA tables that we generated. Usually we are dividing the mean squared of the effect, which in this case is sex, by the mean squared error, or residual, the mean squared effect by the mean squared residual to get these F statistics. But how you do that all depends on whether or not you're treating that treatment as a fixed effect or whether you're treating it as a random effect. So what is the difference between a fixed and a random effect? And one of the harder things to get across to people, your textbook spends, approximately 10 pages trying to get this across to you. So I'm going to try and boil that down into a couple of minutes of lecture. We think of a fixed effect as one of two things. A fixed effect is an effect where either one of two things is true. So these are the two conditions under which we treat an effect as fixed. Either the effect has all the possibilities of that effect in the model. So in this case, we have one of our effects is sex. From the standpoint of thinking about rats, this is a binary sort of classification. You are either a male rat or you are a female rat. And so in this case, all of the possible levels of that effect are in the model. We have male and we have female. We don't generally classify rats as anything other than that. So all of the possible levels are included. The other thing that might happen is that you might just have a question where the researcher only deals with a limited number of variables, but those limited number of variables are inherent in the question that the researcher is having. So in this case, there are two fat types. There's fresh fat and there is rancid fat. Fat that is presumably good to eat and fat that is spoiled over time because it's been left out in the temperature for too long. In warm temperatures for too long. And so in this case, these are not necessarily the only two states of fat that are out there, but these are the only two states of fat that this particular researcher is interested in. And so the researcher might also treat this as a fixed effect because the researcher is only interested in fresh fat, rancid fat. He's not really interested in partially rancid fat, really fresh fat versus not so fresh fat, et cetera, et cetera. There's a continuum, presumably, of freshness, but this researcher is only interested in this particular difference. In addition, there's a variety of different kinds of food that you could feed a rat, but once again, this researcher is only interested in their response to fat type. And so this would represent two situations where the situation is fixed. What is it if it's a random effect? A random effect is an effect where the levels are a random sample of the possible levels for that factor. So, what are some possible examples of this? If you are an education researcher, one of the ways in which we classify different colleges is according to this thing called the Carnegie classification system. Within that, we have liberal arts colleges, we have four-year institutions that sometimes offer limited graduate degrees. We have regional universities. We have our two institutions, which are Class 2 research institutions, and we have our 1 institutions, which are Class 1 research institutions. These different classifications kind of represent a continuum in terms of what's expected of faculty, for example. There is hardly any expectation of research for faculty typically at liberal arts colleges, up to huge expectations for research productivity at R1 institutions. As a matter of fact, at some R1 institutions, they don't ever ask you about your teaching when you were there for a job interview. And in some cases, you don't actually ever teach classes except maybe classes at the graduate level. You never see the inside of an undergraduate classroom. So if we were interested, for example, in first-year success rates, we could gather a random sample of liberal arts colleges, four-year institutions with limited graduate programs, regional universities, R2 institutions, and R1 institutions. But we could also, simply because these are less common, these are kind of less common, we could actually just select these three types of universities, in which case this would be a random effect because we're not selecting all the possible possibilities of institution type in our model. We have randomly selected three particular types, possibly because those were the types that we could get the most amount of data from or something like that. And so this would then be considered a random effect because it's a random sampling of the possible levels that are there. But in a similar way, you might have a particular hypothesis that examines just the two extremes. Institutions that have hardly any research expectations of faculty versus institutions that have virtually nothing but research expectations of faculty. In which case you have a particular hypothesis that focuses on one end of the spectrum and the other end of the spectrum, and that's all you really care about. You're interested in making this stark comparison, in which case this isn't really a random sample, it's a very purposeful sample of the possibilities that you are interested in the same way that this researcher is interested in fresh fat versus rancid fat, in which case institution type would not be a random effect, it would be a fixed effect. Mainly not because of reason one, but because of reason two. And so you really have to get in the head of whatever the researcher is asking to know whether it is a random or fixed effect. And the reason that that's important is that affects how you calculate your F statistic. And your F statistic is what we ultimately use to evaluate the significance of the effect. In the gecko analysis that you guys worked on and turned in last Wednesday, you had two factors. One of these factors was season. One of these factors was population. You've gotten some idea of what is going through the head of this researcher. Would these two things be fixed effects or random effects, and why? Yeah.
I think they're fixed effects.
Okay, why? Start with season.
Season is all the possible levels of that effect model.
Are they? Because we have winter,
The question of the researcher has only deals with winter.
summer, spring, and fall. So we haven't sampled all the possible levels of that. There are 4 seasons as we recognize them. I think the seasonal designation that we have is stupid. Have you guys ever thought seriously about when we decide when winter begins? Seasons are key to celestial events, aren't they? When does winter start? Winter starts at the winter solstice. This is when this is the shortest day of the year in the northern hemisphere. So this is usually around December 22nd. Have you been experiencing winter prior to December 22nd? Yeah. Usually by December 22nd, it has gotten cold here in Missouri. When does spring begin? At the equinox, when the day length is equal around the world. That's what equinox means. Actually, it means equal night, but we won't quibble. That usually occurs around March 21st or 22nd, depending on the year. When does summer begin? This is the summer solstice. Have we generally been experiencing summer temperatures by the end of June here in Missouri? And when does fall begin? Once again, depending on the year, this is the autumnal equinox. It seems to me like winter should actually be somewhere at the midpoint between the autumnal equinox and the winter solstice, because the winter solstice represents kind of the low point of winter, not the beginning of winter to me, or the high point of winter if you're looking at how wintry it is. So these are really arbitrary sorts of dates that are put on our calendar because these represent celestial events that we can easily measure. But even calling the beginning of winter December 22nd belies the fact that it's somewhere between September 22nd and December 22nd that we really start to experience what we would consider to be winter. For us, it starts usually end of October, beginning of November, that we generally see our temperatures start falling. So it isn't, the thing that is in this data set is not the full encompassing of these different seasons. And as a matter of fact, it turns out that these data were collected in January and they were collected in June. That's partly due to the fact that that's when researchers, when faculty have the opportunity to leave campus and go do field research. Those first weeks of January before school has started, and then as soon as the semester is over, we have a little bit of spare time in June, but those also correspond roughly to winter temperatures and summer temperatures. So one could argue that this is a random effect because it is a random sampling of the 4 possible seasons that we could look at. Why is this researcher not particularly interested in spring and fall? Well, it's not necessarily too similar to summer data. It's as similar to summer data as it would be to winter data. It's this kind of intermediate temperature which doesn't represent these extremes, and presumably it's the extremes that cause problems for, in this case, ectotherms, organisms that have to moderate their temperature behaviorally. So spring and fall probably don't pose huge challenges for these guys. So this researcher didn't choose winter and summer randomly. He chose winter and summer because these represent 2 temperature extremes throughout the calendar that potentially represent challenges that might affect the evolution or acclimation of these particular species. In which case, the researcher could argue that in reality, these are actually fixed effects because these are the only 2 seasons that the researcher cares about. You were right and you were wrong, which is common in statistics. It all depends on what the question is that the researcher is asking. Population. We had Oklahoma City, and we had, well, really Edmond, Oklahoma is where they were really collected from, and we had Galveston, Texas. Why these 2 populations? Okay, are these the only places that the lizards are? No, they have a pretty broad geographic range in the United States. Once again, then, if that's not the only places where these lizards are, why these 2 populations? Okay, so this is a northern population, and this is a southern population. Is this the northernmost population? No. Is it the southernmost population? No. I could have gone all the way down to Brownsville, down on the U.S.-Mexico border, down at the very tippy tip of the southern part of Texas. So this is not the northernmost population. The northernmost population I know of is Pittsburgh, Pennsylvania. The southernmost population that I can get to without crossing international borders would be Brownsville. So would population be a fixed effect or a random effect? You could argue that this is a random effect because there are a number of northern populations that the researcher could have chosen. Edmond, Oklahoma happens to be one of them. And there are a number of southern populations that could have been chosen. Galveston, Texas just happens to be one of them. Why did this researcher choose Edmond, Oklahoma and Galveston, Texas? Yes?
Right, because it's like the, pretty, yes, it's a northern and a southern population, but relative to where they are, it's not too far from each other.
Well, yeah, they're both plenty far from each other. Trust me, I've made the drive more times than I care to think. Where is Edmond, Oklahoma located, travel-wise? North of Oklahoma City, just north of Oklahoma City. There's also a population at the University of Oklahoma down in Norman, and there's a population at the Oklahoma Zoo, where a friend of mine is the director of the zoo, and I have permission to collect there. But this is a nice, accessible college campus that's relatively safe to work in, et cetera, and it's right on I-35. Actually, 5 minutes off of I-35. Drive to Edmond, Oklahoma, stay in the same hotel. The people at the hotel know me. I go there so often. It's easy to access, and it's the furthest north within reasonable driving distance to where I live. I could sample Pittsburgh, Pennsylvania, and Galveston, But then I would have to drive all the way to Pittsburgh and then go all the way to Galveston. That's a huge ass triangle that I would spend so much time in travel. Why do I go to Galveston? I-35 doesn't go to Galveston. I-45 goes to Galveston. But I-45 goes from Dallas to Houston to Galveston. So I can take I-35 down to Dallas. I can pick up I-45 and go to the Woodlands. What's in the Woodlands? Well, there are geckos, but not nearly as many as there are in Galveston. What's in the Woodlands? My sister lives in the Woodlands. Once again, like 4 minutes off of I-45, and I can go to her house, I can stay for free, and then I can hop back on I-45 and take I-45 down to Galveston. It's about an hour and a half drive coming back, 2-hour drive going there, depending on what time of the evening that I'm leaving. I can sleep there for free, and I can still collect geckos in Galveston because it's relatively close. It's another 7 hours to get from Galveston to Brownsville. That's the problem with Texas. Texas is a huge ass state. So Texas looks like this. Roughly, Dallas is up here, Brownsville is here, Galveston is here. I would much rather go there than go there if I'm going to go. I've collected in Brownsville. It's fine, but it's a really long drive. Unless I have other collection that I'm doing in that area, I would much rather go to Galveston where I have a free place to stay that's within easy access to the site. So these aren't randomly selected sites. They're sites that are selected largely for their logistical ease, but that's not enough to make it a fixed effect. I could have chosen a number of populations that are at the same latitude as Galveston. I could have chosen a number of sites that are at the same latitude approximately as Edmond, Oklahoma. I could have chosen Edmond, Oklahoma. I could have chosen the population at Norman. I could have chosen the population at the Oklahoma City Zoo. I could have collected from any of those. So this makes a pretty good case that this is a random effect. So if you're going to treat these two treatments in the next thing that you do for me in terms of report-wise, you need to treat the season as a fixed effect, and you need to treat the population probably as a random effect. In which case, that's going to change how you evaluate these two effects in terms of calculating the F statistic, because you calculate their F statistics differently. And so in your book, it gives you this table. Generally, what we would do is we would take a fixed effect, we would divide it, I messed that up, didn't I? Fixed effects are divided by the interaction term. Random effects are divided by the error term. I think I flipped that when I wrote it on the board earlier. So if this is season, where A is a fixed effect, if this is season, you would divide that by the mean squared interaction, but the random effect, which would be population, would be divided by the mean squared residual. And so that's how you should treat this, generally speaking. You notice that when they're both fixed, you divide all of them by the residual term. So that is that. And I think that was the last thing that we had to cover as far as this. All of the same assumptions that you would have to test about a single factor analysis of variance, you would also test about a multiple factor analysis of variance. Questions about that? All right, then let's go to R. So hopefully you have all your packages downloaded, and I just read in the RATFAT data file. The RATFAT data file is pretty small, so we could actually look at the whole thing. So when you've got the RATFAT data file read in, and it ends up looking something like this, put up your blue tabs. Blue tabs up when you've got it read in. Blue tabs, blue tabs, blue tabs. One person left. Yeah.
I have it right here.
No file or directory. Is it in the same directory that you're running? What is your working directory?
The same one I always use.
Is everything just in our intro?
Yeah.
Okay. Let me see your data file. Where's your data file?
Our intro, it's right here.
Ah, because you downloaded it, but it's not called ratfat.csv, it's called ratfat.
Okay.
You either need to change this here or you need to change that to CSV. I'm not sure which will work best. Okay, change your data file to .csv so that R knows that it's a CSV file that it's looking for. Yep, put .csv at the end. Now change that back to .csv. I'll bet that fixes the problem. Embedded nulls. Let me see it. No, just type that and let me see how R read it in. Oh my gosh, it didn't read. Oh, okay. All right. So you've got some issues. Go back to open up the file. Can't be opened right now. Re-download it.
From Google.
Mm-hmm. Everybody else got it done? All right, blue tab's down. Let me get this fixed over here, and then we'll proceed. All right, what? Oh, you just opened that in numbers. Okay, don't open it. Don't open it.
Okay.
All right, actually delete all of those rat fats. That's your problem. You opened it in numbers and then closed it, and it saved it as a numbers file. Numbers is stupid. Are not like numbers. All right, re-download it and then don't open it. Okay, now try it again.
You need to move it to my.
Okay, move it to your directory. As you have noticed, R is very particular about the way it receives information. Wait a minute.
So I don't know why I didn't choose that.
I thought you deleted.
I thought I did too.
Right click on that one, or actually go to show it as a list. List. Oh, correct. List. There you go.
I think this is.
That was at 940.
Yeah.
Oh, that's the one we just did. Okay, so it's that one. Okay, now try it again. Where's your drive? Okay. All right. What the heck? Unless you trust the source. All right. Yeah, I'm trying to fix a problem. Where is your desktop? Go find your desktop. All right. Okay, all right. This is stupid. Give me a minute. Open up your email. Get rid of all the rat fats in our intro folder. And I've just sent you a version of the file. Drag that over and see if that works. I'm not sure why the one that everyone else downloaded is not working. Okay. Check that it's in there. Okay, now try it again. There it is. Do that. All right. Oh, awesome. Okay. So we've seen the data file. What else might we want to know about the data file? Somebody other than Karis. Structure. Okay, run structure. Why do we want to run structure? Okay. It'll tell us not only what the columns are, but it'll also tell us how R is treating those columns. So let's do that. And what we should see is that it is treating fat as a character, sex as a character, growth as integers, and growth 2 as integers. So growth is just the original data set, and growth 2 is when I rearrange the data to make the interaction significant. So we're going to just look at the original data as they currently are. So what do we might want to do to these data? What might we want to do to these data? There's no filtering necessary because the data set are just the data that we have. We want it as not a character, we want it as a factor. And do we want to do that just with fat? We want to do that with sex as well. And then after we've done that, what do we want to do? We want to make sure that it did it. When you've done that successfully, put up your blue tab. Orange tab. What's up?
This one's working, but it keeps giving this error, attempt to use zero link variable name. I don't know what that means.
What are you doing? Where are you at?
I haven't started that yet, so I was trying to fix it. But I've already, like, all this stuff worked.
Yeah.
Like, reading the page just keeps giving me that error.
Oh, because it's getting that. How are you running the script? Are you using command return, or are you doing something else?
Or the command return.
Okay, so when I had that data file,
Like, everything works. It just keeps.
that's weird. Yeah, let's look at the whole thing. Yeah, I'm not sure why that's doing that. All right, just continue. It's probably just an error that's telling you something that's not important. We'll see if it gives you a problem later. Just put up your blue tab when you've got this thing done. Okay, yeah, so it's still working. Something wrong with your variable names, although I don't know. They look fine to me. Okay, all right. Okay, tabs down. Notice that when I talk about these things, I use the same language that R does. I talk about all the possible levels of that effect. So when we think about a factor, we can think about factor 1 is sex, factor 2 is fat type, and factor 1 is fat and factor 2 is sex. And both of those things have two levels, fresh versus rancid and male versus female. So what we now want to do is do what? What's the next step? So we've read in our data, we've checked it, we've altered it in ways that we want to alter it. What would be our next thing that we want to do? Yeah.
Specify the model.
Why would we want to specify the model at this early stage?
Saves us some typing later.
Save us some typing later, and we want to get what out of the model? So we can test some of the assumptions. We want to get the residuals. Why do we want the residuals? Nope. One of the tests of assumptions. Not homogeneity of variances, so it must be normality. Okay.
Are the assumptions the same for 2 ANOVA as they were
Yep.
for 1?
Yep, same. So let's specify a model. So in this case, what we're going to do is, I'm just going to call this model. You can call it analysis, you can call it X. I don't really care. It's up to you, your personal preference. Give ourselves an assignment operator. How are we going to specify this? Yeah, so what do we usually use for ANOVA? AOV. And in this case, what do we want as the response variable? Growth is the response variable, and it is affected by what? Sex and fat. Okay? And what are we going to be working on? You need your data frame. Okay? So let's run that. I get no error. Let's get a summary of that. We've clearly done something wrong. Why do we know that we've done something wrong? When we look at this ANOVA table, how do we know we've done something wrong? Our degrees of freedom, we had 4 different subsets, so our total degrees of freedom should be 11, and our degrees of freedom are 9, 10, 11. Yep, so degrees of freedom are correct. A good idea, though. Checking degrees of freedom is always a good first step. This is the ANOVA table down here that applies to this particular analysis. We see that we observe 3781 for the effect of fat, for the effect of sex. We have 61204 for the effect of fat. Our residual is 12585, but what we have over there is 11666. Why? What's going on?
We don't have an interaction term?
We don't have an interaction term. So when you don't specify the interaction term, whatever variation is accounted for by the interaction just gets dumped into residual. And so we didn't do something about the way we were typing our model in that left out the interaction term. So if we want to add the interaction term in, we have to do sex, then use the asterisk to basically represent a multiplication by fat. So this is the sex by fat interaction. So run that and get the summary of the model. And what we find is that now the model has the effect of sex, it has the effect of fat, and it has the fat by sex interaction. And you see that all of these numbers now match up what we calculated by hand last week. So when you specify a model that has interactions, you have to include the interactions explicitly in your model. Make a new model, model 2. AOV. And we're still going to be looking at growth as it is determined by, but in this case, just put in the interaction term, sex by fat. Data frame equals whatever your data frame name is. Run that. You should get no error, and then change your summary to summary of model 2, so we get the output from model 2. When you've completed that and have the output from model 1, the first model, and the output from model 2 on your screen, put up your blue tab. Yeah.
Were those the right formulas for the ones you're talking about?
Fixed effect? No, sorry, because I messed up. I flipped them in my head. Yeah, this is, oh no.
I flipped it from what you
Oh yeah, yep, that's correct. Okay. Yep, that's correct. What do you notice about these two ANOVA tables? They're exactly the same. If you tell R that you're looking for an interaction, it assumes that there's a main effect of the first factor and that there's a main effect of the second factor. So you don't have to write out sex plus fat plus the interaction. You can just say, my model is a factorial model that has an interaction term, and when you do that, it basically automatically assumes that the two effects that are in that interaction are actually going to have their own individual effects. So you can save yourself a little bit of typing by just typing in the interaction and forgetting about the individual variables themselves. This will become important when we do analysis of covariance, because we're going to separate the covariate from the regular factors using a plus sign, but we're still going to use this interaction term to define the main effects. So we have this model, and we could use either model or model 2. They're both the same. So now what's the next thing that we want to be doing? What's that? Okay, so we might want to get the residuals. So we can make a new variable. I'm just going to call it res because I'm lazy. And these are just the residuals from model or model 2. Doesn't really matter. If you run that and get no error, then get it to just print out what the residuals are. You should have 12 residuals. Some of them should be positive, some of them should be negative, and those are the residuals. Blue tabs up when you got that to run. Everybody's blue tabs are still up from before. What's the purpose of getting residuals? So we can test normality. So let's put some annotations in here. How do we test normality? Shapiro test on what? On res. P-value. Blue tabs up when you got the p-value from the Shapiro-Wilk test. Oh, here. Yeah, just Shapiro. Just start typing in Shapiro and then use tab complete. All right, everybody get that? What does this tell you? Anybody? It tells you that they're not significantly different from normal. Is that the same thing as saying that they're normal? No, why not? There's still the possibility that it's not normal, especially because why in this particular case with this particular data set? We have a really small data size, a really small sample size. So how can we explore this in better ways to see if we actually believe this statistical result? We can visualize it with a histogram. What do you guys think about that? You know, that's not terribly reassuring, is it? How else can we look at this? QQ plot. But when we look at the QQ plot, what does the QQ plot look like? Once again, the solid line is what we would expect to see, and the dots are our actual values. We see that with the exception of these 2 points here and this point here, things lie pretty much along the line. And so looking at the QQ plot, the QQ plot doesn't look too askew. So we would probably just proceed under the assumption that it's not so non-normal that we need to do something about it. What is the next thing that we need to do? Next thing we need to do is test homogeneity variances. So we do this with, yep. And the second one, not the first one, because the first one doesn't work any longer. And we're going to do this on our model. Whoa. You'll see that it works for model 2, but not model 1, because of the way we specified it. And we find that there is not a significant difference for Levine's test. P is 0.4. Do we believe this result? You kind of want to believe this result because Levine's test is the thing that bites you in the butt all the time, but should you believe this result? Why or why not? Why?
Well, you should probably have to check of your own just to see because it's very, very close to the 0.5 mark.
It's not very close at all.
Yeah, I don't know. You should believe it.
I don't believe it, actually. Why do I not believe it? What's our sample size? What's our operational sample size here? So we're comparing the variance of one subgroup versus the variance of another subgroup versus the variance of the third subgroup versus the variance of the fourth subgroup. What is the sample size within each of those subgroups? It's 12 for the whole experiment, but within each subgroup, it's 3. What are the odds of you finding a significant difference among variances if you only have a sample size of 3 for your comparisons? Not very likely, is it? Homework for Wednesday. We've gotten to the point where we have a non-significant result from the Levine's test. Build me a visualization that will give us some idea whether or not we should trust this finding or not. So create a meaningful graphic that will illustrate this. You might use things like Summary SE to generate the raw data, et cetera, et cetera. On your tabs, blue things that went well, orange, things that didn't go so well, and hand those in, and I will see you on Wednesday. Are you feeling better about coding in R now? Feel more natural to you? Okay, good.